Hello and welcome. Today, we're going to embark on a journey into the heart of electronics to understand one of its most fundamental and fascinating components, the capacitor. You've almost certainly heard the name, and you use devices that contain hundreds, if not thousands, of them every single day. But what is it, really? How does this little thing actually work? By the end of this video, we're going to use this one simple diagram to completely unravel the mystery. We'll go step by step, explaining every single term and every part of the process in plain, simple language. You won't need any prior knowledge of physics or electronics. Let's get started. What we're looking at here is a very basic electrical circuit. A circuit is just a closed loop, like a racetrack, that allows electricity to flow. Our circuit has three main characters. First, we have our power source. Second, we have the path for the electricity to travel. And third, we have our star player, the capacitor. Let's meet each of them individually. Let's start with the engine of our circuit, the power source. Here, it's represented by this symbol, which is the standard symbol for a battery. It's labeled voltage. So, what is voltage? The best way to think about voltage is as electrical pressure. Imagine a water pump. A pump creates pressure to push water through pipes. A battery does the same thing, but for electricity. A battery has two ends, or terminals. You can see one is marked with a long line and a plus sign. This is the positive terminal. The other is marked with a shorter, thicker line and a minus sign. This is the negative terminal. The secret to the battery's power lies in chemistry. Inside the battery, chemical reactions cause a massive surplus of tiny particles called electrons to build up at the negative terminal. It's like a room getting incredibly crowded. At the same time, the positive terminal is left with a severe shortage of these electrons. It's like an empty room, waiting for people to arrive. This imbalance, this crowded negative side and empty positive side, creates a powerful desire for things to even out. This electrical desire or pressure is what we call voltage. It's the push that will get the electricity moving once we give it a path. Now, let's talk about what's actually going to be moving. See these little blue dots? Our key tells us these are electrons. Electrons are real, subatomic particles. They are incredibly tiny, and they carry a fundamental negative electrical charge. The black lines in our diagram represent the wires of our circuit. These wires are made of a conductive material, like copper. What makes a material conductive is that its electrons aren't all tightly bound to their atoms. Some of them are free to roam around. You can think of the wire as a hollow tube, and the free electrons are like marbles inside the tube, ready to be pushed along. The organized movement of these electrons through the wire is what we call an electric current. So, when we say electricity is flowing, what we really mean is that billions and billions of these electrons are moving in a coordinated way through the wire. And now, let's turn our attention to the main event, the capacitor. At first glance, it looks like a break in the circuit, and in a way, it is. A capacitor, in its most basic form, is made of two main parts. First, we have these two thick, black vertical bars. These are labeled conductive plates. Just like the wires, these plates are made of a material that allows electrons to move onto them and across their surface with ease. But here is the most critical feature of a capacitor, the part that defines its entire purpose. Look at the space between the two plates. This space is filled with a material labeled dielectric. A dielectric is an electrical insulator. An insulator is the exact opposite of a conductor. It's a material that does not allow electrons to pass through it. Think of it as a solid, impenetrable wall or a giant dam built right in the middle of our electrical racetrack. This wall is the whole secret to how a capacitor works. Okay, all the pieces are in place. We have our battery ready to push, our electrons ready to move, and our capacitor waiting in the middle. Let's connect the circuit and see what happens in slow motion. The instant the connection is made, the voltage from the battery goes to work. The negative terminal, which is overcrowded with electrons, begins to push them out with great force. The electrons are repelled from the negative terminal and start flowing along the wire. We can follow their path, indicated by the arrows labeled flow of electrons. These electrons travel along the wire and arrive at the right-hand conductive plate of the capacitor. But when they get there, they hit the wall. They've reached the dielectric, and they cannot pass through it. So, what happens? They have nowhere to go. They simply start to accumulate, or pile up, on the surface of this plate. As more and more negatively charged electrons gather here, this entire plate becomes negatively charged. Now, something equally important is happening on the other side of the circuit at the exact same time. Remember the positive terminal of the battery? It has a shortage of electrons and is desperately trying to pull them in. It exerts an attractive force on the electrons and the wire connected to it. So, it starts pulling electrons from the left-hand conductive plate of the capacitor. These electrons are stripped away from the left plate, travel down the wire, and are drawn into the positive terminal of the battery, completing the circuit's loop. Now, think about what happens to that left plate. It started out electrically neutral, with a balance of positive and negative charges. But now, we've removed a huge number of its negative electrons. When you take away the negative charges, you're left with a net positive charge. So, this plate becomes positively charged, as shown by all the plus signs. It is absolutely vital to understand this point. No electrons ever jump across the dielectric gap inside the capacitor. The action is a transfer. The battery moves electrons from one plate, around the circuit, and deposits them onto the other plate. So now look at the situation we've created. We have a plate full of positive charge and a plate full of negative charge, sitting incredibly close to each other, but separated by the dielectric insulator. This separation of positive and negative charge creates a powerful, invisible field of force in the space between the plates. This is called an electric field, represented by these red arrows. The field points away from the positive plate and towards the negative plate. You can think of this electric field as stored tension. It's like stretching a rubber band. The energy you used to stretch it is now stored in the tension of the band, ready to be released. In the same way, the capacitor has taken the energy from the battery and is now storing it in this invisible electric field. This is the primary job of a capacitor, to store electrical energy. It's a tiny energy reservoir. Before we wrap up, let's clear up one common point of confusion. You might have noticed that the flow of electrons is shown moving counterclockwise, from negative to positive. But there's another arrow, this purple one, labeled conventional current, which is shown moving clockwise, from positive to negative. Why are there two different directions for current? This is purely a historical accident. When early scientists like Benjamin Franklin first started studying electricity, they didn't know about electrons. They had to guess which way it flowed. They guessed that it was a flow of some kind of positive fluid moving from the positive terminal to the negative terminal. This became the established convention, and we still call it conventional current. Much later, physicists discovered the electron and realized that it's actually the negatively charged electrons that move, and they flow in the opposite direction. This is the electron flow. So, why do we still use the wrong one? Because by the time the electron was discovered, the convention of positive to negative flow was already deeply embedded in all the textbooks, equations, and circuit diagrams. So, engineers and technicians today typically still use conventional current. It doesn't really matter which one you use, as long as you're consistent. They are just two different models to describe the same electrical phenomenon. So, let's put it all together one last time. First, the battery provides the voltage, or electrical pressure. Second, this pressure pushes electrons out of the negative terminal and pulls them into the positive terminal. Third, electrons pile up on one conductive plate of the capacitor, making it negative. At the same time, electrons are removed from the other plate, making it positive. Fourth, the dielectric insulator in between prevents any electrons from crossing the gap. And fifth, this separation of charge creates a powerful electric field between the plates, which is where the capacitor stores its energy. This charging process happens incredibly fast, and it continues until the voltage across the capacitor's plates becomes equal to the battery's voltage. At that point, the push from the battery is perfectly balanced by the pushback from the charged capacitor, and the flow of current stops. The capacitor is now fully charged, like a tiny, temporary battery, holding its energy and waiting for a chance to release it. And that is the essence of a capacitor. It's an energy storage device that works by separating charge across an insulator. From smoothing out power in your phone charger to creating the flash on a camera, these simple but brilliant components are absolutely everywhere. We hope this deep dive has given you a new appreciation for the elegant physics at work inside even the simplest electronic components. Thank you for watching.